Welcome, AP students. I trust you're doing well. Today we're going to actually wrap up our Unit 5 review. First off, we're going to talk a little bit about the K constant. We use K constant quite a bit throughout this term, and we realize that in equilibrium, K is unitless, so we didn't have to worry about the units. However, in this particular section, the kinetic section, K has a specific, so hopefully you remember that, a specific units that are assigned to it. So when we look at this right here, we have our zero order. So remember we talked a little bit about order, and you can have zero order, first order, second order. Those are very common. Third order is not as common. And then you get the fourth order, that is extremely rare, and above that is pretty much non-existent. You might be able to find a record of maybe a fourth order or something like that, but nothing much more than that because of the energy required and the alignment for the reaction to happen. But when you look at calculations involving the K constant and our rate law expression, when you look at the units for zero order, this is your unit. It's molarity with divided by seconds, and that's what the -1 is because it came to the top, molarity per second. First order is just S -1, which would be cycles per second. And second order reaction would be right here. Molarity to the -1 and seconds to the -1 in this case, which would mean they would both be in the denominator. And if you looked at a third order, it would be M-2 and second, and if it was in second, second -1. So M-2, S-1 would be for third order. So those are really just things you should be familiar with. You do have, for kinetics, a K constant has specific values. Now we're going to look at reaction order, and specifically we're going to spend time looking at zero, first order, and second order. The one that we will use mostly in AP and that you should be very familiar with for the AP exam is this one right here, our first order reaction. We'll look a little bit more at that. But when you look at the straight line plot, that's the real important one we're going to spend a little time on. But integrated rate law. So when you look at this, if you get your formula sheet out, you are given a little bit of information on kinetics. And remember, it wasn't a lot. You got the half-life for first order reactions, because that's typically the one that you'll see the half-life for. You get first order and second order integrated rate law. So when you look at what is the integrated rate law, it's in the form of a line, the slope-intercept form. And here you have for zero order, you have the concentration final equals the concentration original minus KT. When you come to the first order, and this is one that is used a lot, you have the natural log of the concentration final equals the natural log of the concentration original minus KT. And then our secondary, it's 1/. And that's how you know the second order reaction, because it's 1/. And they're all straight lines. If you're just looking at the plot of the line, the second order is going to be going upward. And when you look at the zeroth order and the first order, they're going down. When another way to look at this is a lot of times you'll be given a graph. If you look at the y-axis, you usually will see the concentration. And if you see 1/, concentration of A, when you just look at that, then you know you have a second order reaction you're dealing with. If you look and you see something like this, natural log of the concentration of A, right away that's first order. if you see concentration of A, just plain concentration, that's zero order. So there's a little tricks to if you see a graph that you can automatically understand. Here is our half-life formulas right here. And this is important in that this is the one most commonly used in AP Chem. When you look at 0.693, what is 0.693? That's the natural log of 2. And that's how our formula sheet, if you look at our formula sheet, it gives it to us as, actually they give it to us as 0.693, but it is the natural log of 2. So this is a pretty important slide right here. Hopefully you have some of this stuff in your notes already, and it's just refreshing your memory on it. All right, so graphs and reaction order. So they're all straight lines. So when you look at the straight line and the y-axis is concentration of A, that means it's zero order. If it's a natural log of the concentration of A, that's first order. If it's 1 over the concentration of A, that tells you right away. You don't have to really do much more. You just see that and you know it's second order. But one of the things that I want to look at with you is one way that we can switch these around, and this is really important. We're going to focus on this one right here. Hopefully you remember this already. So I'm just going to rewrite it right here. So I'm going to go the natural log of the concentration of A equals negative KT plus the natural log of the concentration of A original. That's the original amount that you had at the beginning. All right. So I am going to minus this off. So when I minus this, I'm going to have right here, I'm going to have natural log of concentration of A minus the natural log of the concentration of O, and that's going to equal negative KT. When you talk about minusing a natural log, there's something that you could do. I could also redo this as such. I can go the natural log of A divided by the natural log of, and I could put it like this, equals negative KT. Hopefully you remember that. So now that I have it in this form, I can get rid of the natural log. So remember, I could get rid of the natural log by bumping this up on E. So I could rewrite this as the concentration of A divided by the concentration of A original equals E raised to the negative KT. Hopefully this comes back to you. This is a very common form. That's why I wanted to take a moment on this. Very common form. So if I take my slope-intercept form, and you don't have to memorize it, you have it on your formula sheet actually written in this form right here. This is on your formula sheet. You just have to know that you can pull the natural log and put it as division, and that's the same as this section right here, as a natural log of A minus the natural log of A original. And once I put it in this form, I can rewrite it into this form here. And when I'm in this form, it is, a lot of times I'm solving for my final concentration. So another thing that I could do is multiply both sides by the original concentration. Cancels off here. So this form right here is really important. You'll use this quite a bit. The concentration final equals the concentration original multiplied by E raised to the negative KT. And this is a very useful formula. And we're going to look at that here in a little bit. So very important to be able to use that. Another thing here that you'll use a lot, because the first order reaction is given quite a bit for decay, half-life decay problems. Another thing is that you can find, and this is provided for you right here on your formula sheet, 1/2 equals, T to the 1/2 equals 0.693 and divided by K. So you could also rewrite this as K equals the natural log of 2 divided by the half-life, and that's very useful too. You'll see that as we go through. All right, so having done that, hopefully that rings a bell, maybe helps you remember that. We've done a couple of problems like this originally, so let us continue. Here is a little view of those graphs that I was talking to you about. Straight line, you see this right here, concentration of A, that's 0 order. You see the natural log of A, that's a first order. You see 1/A, that's second order. You don't really need to go much further than that. This is also a clue too that you have this, the line going up in a positive slope rather than the two which are negative slope. But nevertheless, once you see the y-axis units, you should know right away what type of reaction you're looking at. All right, here is an example problem. Maybe you would like to pause the video, try and work this out on your own, and kick it back on, and we'll work through it. So take a moment and do that. All right, well, hopefully you did. So let's just begin by looking at this problem. It says iodine 131 decays by beta emission and has a half-life of 8 days. So I know right away T 1/2 equals 8 days. And proceeds by first order reaction. So they straight up tell me what the order is. If I begin with 125.00 grams of iodine, how much is remaining after 8 days? All right, so I could get my formula sheet out and realize that I'm going to have to do a little bit of work on this particular problem. So I'm going to rewrite my integrated rate law for first order, and I'm going to write it like this. I'm going to go the natural log of A divided by the, and this is the concentration of A original, and that's going to equal negative KT. Well, I have my T 1/2, so I know that it says T 1/2 equals natural log of 2, which is 0.693. So 0.693 divided by K. Well, I have T, but I don't have K. And as I look over here at my integrated rate law, I have to have K. So let me just rearrange this. So I'm going to go K equals 0.693 divided by T 1/2. And I was given that. So now, therefore, K equals 0.693 divided by 8. So K equals, if I get my calculator, I get 0.693 divided by 8. And I have 3 significant figures. Remember, 8 is a direct count, the number of days. So it's unlimited significance. So I have to go with the 3 significant figures. So I have 0.0866. So K equals 0.0866. So that's good for right now. All right, so I really don't want to work with the natural logs. I'm going to change this whole thing around, and I am going to bump this around. So I'm going to get, and that's going to be over the concentration of A original equals E to the negative KT. Well, I don't want to do the solving for in the denominator, so I'm going to eliminate that. I'm going to multiply both sides by A original, concentration of A original, and I'm going to get rid of it here. So now I can rewrite this. So I have the concentration of A, which is going to be the final concentration, equals concentration of A original times E raised to the negative KT. Now I can get some things done and I can actually solve this and know how much is going to be remaining at the end of 28 days. All right. And that's what my time is. My time is the number of days. So I'm going to plug this in now. So my final concentration is going to equal my concentration original. It tells me it right here. So I'm going to go 125.00. And then I'm going to go E. It's going to be multiplied by E. And then I have negative. And my K, I solve for it right over here. It is 0.0866. And my time is 28 days. 28. And you plug this in the calculator exactly how that is. I should actually come over here and put this in brackets because you want to keep that all happening together. So if I plug this in, and remembering 28 days is a direct count, I do not need to have significance on that, so it's unlimited. So my significant figures is limited by that 0.0866, which is 3 significant figures. Let me plug this in. So I go my 125.00, and I'm multiplying that by E raised to the negative, and I'm going to go parentheses, 0.0866 times 28, close parentheses, equals. And I come out to a pretty long number, 11.06197705, but I only have to have 3 significant figures. So my concentration final is going to equal 11.1 grams. So that is my final answer after 28 days. So I'm going to go from 125 grams down to 11.1 grams. There's another way you could do this. It's very time consuming. You probably don't want to do that. Is just go every 8 days and divide what you have left in half every 8 days. And you can do a whole collage of work to get that. But this is the simplest way. It's not extremely difficult once you have practiced the process. All right, so hopefully you did that, you got that, and you follow us on that. I do have a little bit of bell work activity for us pertaining on this for today. So hopefully you watch this video before you attempted it. All right, so elementary reactions and molecularity. That's a big word there, molecularity. And you have unimolecular, bimolecular, and termolecular. And that is talking about the number of reactants that you have. You have 1 that's unimolecular, you have 2 that's bimolecular, you have 3 that's termolecular. Now when you go to have 4, that's why it gets, and when you look at the rate law, that would be going to 4th order. That it's really non-existent because now I've lined 4 things up to have collisions happen all with enough energy and in the right position is not really possible to do. So termolecular is about all you have, and that's your 3rd order reactions. And here it talks about the rate law for them all, and you can have them in different formats, just like that. You could have A, B, and C all to the 1st order in regards to themselves, or you could have 1 to the 3rd order, or you could have 1 to the 2nd order and 1 to the 1st order, because it can go in either one of those ways. Rate and reaction mechanisms. So reaction mechanisms is a sequence of reaction steps. And that's what we looked at. Sometimes you have 2 steps, 3 steps, 4-step reaction processes, and you're looking at trying to get the rate law off of them. So let's look at some factors that affect the reaction rate. So first off, we have the rate of collision between the reactants. So that makes sense. If you can't have a collision, you're not going to have a reaction. So that's a factor that can affect. And it depends on how many reactants you have. Maybe you have 2 things and you have a high concentration of one and low of another. So that's going to affect your overall reaction. Collisions in the right position and energy is really important. They have to have enough kinetic energy to allow the reaction to continue. The concentration of the reactants increase. If you increase the concentration, you're going to increase the possibility for them to contact with each other. The surface area, so if it was, say, a solid that you were introducing into a liquid, If you have it ground into finer powder, now you've increased the chances of collision, so now you have increased the actual rate of the reaction. And then finally, temperature. The Arrhenius equation, if you remember, we did not use the Arrhenius equation, but we used it as a justification because it is directly proportional to the temperature. So the rate is proportional to the temperature. Real important concept. So what is the rate determining step? Hopefully you remember that, the slow step. So you have to find the slow step. That is your rate dependent step, is your slow step. So your overall rate reaction must agree with it. Doesn't have to have it. Remember, it has to have the species that are listed in the final, but it has to still agree with the slow step. So here, let's look at slow step, fast step. So this slow step is your rate dependent step. So your overall reaction is here. Your rate law must agree with this right here, but it has to involve the slow step. So when you look at the slow step, it works out. This, in this case right here, you have a second order reaction, ozone to the first and nitrogen monoxide to the first as well. So let's look at an example. Maybe you'd like to try this and pause the video. We'll break it down together. All right, hopefully you took a moment on this. So here I have my overall reaction. So my rate law has to follow my overall reaction. It doesn't have to have each one of those components, but it must follow that and also involving the slow step. So when I look at my slow step, I could go like this. I could write my rate equals K times the concentration of N2O2 and O2. And that is my slow step, my rate determining step. Now let me compare it to my overall reaction. O2, check, check. Well, I can't keep N2O2 because it is not in the overall reaction. The overall reaction has NO. So this has to be taken out. So I have to look back, how did I get the N2O? So I look back on this step here and look at how it was derived. So now I could replace that. So I have NO and there is a coefficient of 2 there, so I raise this to the second. So now I can rewrite this. So my rate equals my K constant times NO squared and O2. And that is my rate law expression. So please, hopefully you can look back in your notes and look at, we've done a lot of examples of these, even to some raised to the 1/2 power, if you remember that. But please look back on that. And this is one where the slow step did not exactly match the overall reaction, but we still honored the slow step in forming our overall rate law expression, and that is important. So identifying intermediate. So remember, what is an intermediate? An intermediate is something that appears but is consumed in the reaction. So when you look at this right here, and a lot of times they might ask you to identify an intermediate. So when you look at this reaction mechanism that's here in these elementary steps, you see that the only things really on either side that you could cancel off would be the dinitrogen monoxide, N2O. Just cross them off, and that is your intermediates. So intermediates, here is another mechanism. And notice in this here, there's a lot of intermediates in this particular example here. So you see NH2Cl is canceled off on both sides, OH minus is canceled off, N2H5 plus is canceled off. So those are your intermediates. If you had to identify from a reaction mechanism, cross off the things you crossed off are typically your intermediates. Now you could have catalysts, and we'll talk about that here in a second. So a catalyst, remember what a catalyst is. It speeds up the reaction without being completely consumed in the reaction. So it's not really a part. It can be a part of an elementary step, but it is back again and in a product so that it could be reused. And that's what it says here. Because it's present initially and then reforms as a product elsewhere in the process. So here you have the iodine ion consumed, and then here you have it reappear, and that is a catalyst. And you could have to identify a catalyst. So why are catalysts so important? Remember, it lowers the activation energy. So here is this activation complex. Without the catalyst, look at the amount of energy needed. Got to go all the way up here. But if you have a catalyst, look at how much you spare of energy. It lowers the activation energy and allows it to complete and move through the reaction at a much lower energy. So catalysts are very important. So catalysts, there are basically three types of catalysts. A homogeneous catalyst means it is the same phase. So it's either both liquids or maybe they're both gases. The reaction's a gas and the catalyst is a gas, or it's a liquid and the catalyst is a liquid. Maybe it's an ion, manganese ion inside of a solution. Then you have heterogeneous. Heterogeneous is a different phase. So you might have aqueous and you might have metal, platinum or solid manganese, something like that. And then you have enzymatic, where you have the activation site on an enzyme, and that is in macromolecules of amino acids in living organisms and living tissues. So those are your three types of catalysts that you can have. Last thing in this particular section is a graph of endothermic and exothermic, and we're going to pick that up on Friday as we begin Unit 6. So here is a endothermic versus an exothermic. So endothermic absorbs energy. So if you notice, the products are at a higher level of potential energy than what the reactants were. So the products are storing a lot of energy in them. When you look at exothermic, the products are releasing energy. So the reactants actually had more energy potential than the products. So in the formation of products, it released a lot of energy. And that is favorable. So here you have a process and the graphs are completely different. So hopefully you are remembering this, jogs your memory. When you look at these two graphs, you might have to identify which graph is an exothermic reaction, and you would have to pick this one, obviously. Even if it doesn't list it, it wouldn't list it, but the products are in a lower state of potential energy than the reaction. And ladies and gentlemen, that is it for this particular section. So we are finished with our review of Unit 5, Kinetics, energy and rate laws, and calculations of half-life. So hopefully you enjoyed the videos. Hopefully it brought back a lot of the information for you. And please don't forget, you have the AP Classroom quiz. There are 2 quizzes. They're both in there. One question is a free response question, but it would not allow AP Classroom because these are really strategically picked. I got this particular question from the exam, a practice exam that was created by AP Classroom and AP Central. So please make sure you don't miss that. There are, I think it's 19 questions, multiple choice with the key concepts, and then 1 free response. And that's due Thursday, 8 p.m. So once again, thank you for watching. Go in peace.